electromagnetic waves and their generation. We know a changing electric field produces a changing magnetic field. On the other hand, a changing magnetic field could produce a changing electric field. And this phenomenon gives rise to a transverse wave known as electromagnetic wave. The time varying electric and magnetic fields are mutually perpendicular to each other, and at the same time they will be perpendicular to the direction of propagation of the generated transverse wave. In this composite wave, the electric vector is responsible for the optical effects of. Hence, this is called light vector. In the electromagnetic wave, the electric field vector is responsible for optical sensation. That's why it is called as light vector. Here, it is shown the propagation of the electromagnetic wave by means of mutually perpendicular electric field and magnetic field, and these two are perpendicular to the direction of propagation of the wave. It is the c bar is the speed, or here it is being in a specific direction, we can call it as a velocity vector. And importantly, in this electromagnetic wave, the mutually perpendicular fields E bar and B bar are always in phase. They oscillate perpendicularly, but they will be in phase. And then if E bar and B bar represent the electric field vector and magnetic field vector in the electromagnetic wave, the term or the quantity E bar cross B bar is always in the direction of propagation of the wave. Here the cross product vector of electric field vector and magnetic field induction vector. You know, cross product vector is non-commutative, therefore order is very important. E bar cross B bar is in the direction of propagation of the wave. The electromagnetic wave propagating in the positive x direction may be represented by its electric field component and the magnetic field component by its instantaneous values as E equal to, it's along y axis, it is shown earlier in our figure, and B is taken along z axis, and E equal to E suffix y equal to E naught sine of omega t minus kx. It's a sinusoidal function. It's a varying, time varying function this is. And this electric field vector at any instance is E equal to E naught sine of omega t minus kx, and B equal to B naught sine of omega t minus kx. In this, the E and B stands for instantaneous values of the fields. E naught and B naught stands for the amplitudes of the fields, the maximum values, E naught and B naught. And omega is the angular frequency of each, and k is angular wave number, which is equal to 2 pi by lambda, where lambda stands for the wavelength of the wave that is propagating. So E equal to E naught sine of omega t minus kx, B equal to B naught sine of omega t minus kx represents the electric field and magnetic field instantaneous values in the given electromagnetic wave propagating along positive x-axis. And then let's understand the conduction current, displacement current, modified Ampere circuital law, and very importantly Maxwell's equations. We know in a conductor, the electric current that arises due to flow of electrons is called conduction current. We have studied much about this conduction current in all our conductors, in our current electricity, and in any other case earlier. The conduction current concept, we are well aware of this. It is due to flow of electrons in a conductor. So conduction current, denoted by I suffix c equal to rate of flow of charge d by dt of q. What is displacement current? It's a new introduction. Now in a circuit that the current that arises in a region due to time rate of change of electric flux is called displacement current. So in a circuit, especially in a circuit when capacitor like the element is present, a device if it is present in our circuits, now the current that arises in a region due to time rate of change of electric flux is called displacement current, and it is given by I suffix d equal to epsilon naught into d by dt of electric flux denoted by phi suffix e. Here epsilon naught is absolute permittivity of the free space. When a capacitor is charged or a charged capacitor is allowed to discharge, the electric flux between the plates of the capacitor changes with the time, and it gives rise to the displacement current between the plates. The concept of displacement current comes into our explanation, comes into our study in order to apply the Ampere's circuital law in a circuit with accuracy. The Ampere circuital law in its original form had a limitation. When elements like a capacitor are present in our circuits, the Ampere circuital law is failing. Therefore, the Ampere circuital law needs a modification, and that modified Ampere circuital law by using the concept of displacement current is as follows. It states that the line integral of magnetic field, that is B bar, over a closed path is equal to mu naught times the sum of the conduction current and the displacement current threading the closed path. Earlier we have only states that the line integral of magnetic field over a closed path is equal to mu naught times of the current that is enclosed, only simply conduction current that is enclosed. But now it's modified as the sum of the conduction current and the displacement current threading the closed path. So the modified Ampere circuital law, or simply called Ampere Maxwell's circuital law, it is the other way it is called like that. Ampere Maxwell circuital law is the integral of B bar dot B dl bar over a closed path is equal to mu naught into here the sum of the conduction current and displacement current. Previously we have integral of B bar dot dl bar over a closed path is equal to mu naught times of I. But now in our circuits it is introduced not only conduction current but also displacement current. Remember, displacement current arises due to rate of change of electric flux in a region of the circuit. Better example is in case of capacitor, as a capacitor is charged or a charged capacitor is allowed to discharge, the rate of the electric flux between the plates takes place, and that leads to conduction current. So our modified form of Ampere circuital law is integral of B bar dot dl bar is equal to mu naught times of the sum of the conduction current and the displacement current in the given closed path. And Maxwell's equations, it's a very important concept for us. We have our recent entrance, in recent NEET exam, we have this question, Maxwell's equations. Previously in AAPMT number of times this question is present to recognize a particular equation which is one among the Maxwell's equations. Here the following four equations which describe the laws of electromagnetism are called Maxwell's equations. Integral of E bar dot ds bar over a closed surface. here this symbol you have to read as closed surface. This is surface integral. Integral of E bar dot ds bar over a closed surface is 1 by epsilon naught times of the net charge enclosed. This is Gauss law in electrostatics. Integral of E bar dot ds bar over a closed surface is 1 by epsilon naught times of the net charge enclosed in the surface. This is Gauss law in electrostatics. Next, integral of B bar dot ds bar over a closed surface is equal to 0. This is Gauss law in magnetism. And this integral is being equated to 0. It implies the magnetic poles always exist in pairs. This conclusion of magnetic poles always exist in pairs can be explained from this statement. That's what we say Gauss law in magnetism. That is integral of B bar dot ds bar over a closed surface is equal to 0. Then integral of E bar dot dl bar over a closed path. This is a line integral. Integral of E bar dot dl bar over a closed path is equal to minus d by dt of the magnetic flux phi suffix b. This is magnetic flux, and negative sign is in accordance with the Lenz's law, and this is called Faraday's law of electromagnetic induction. Integral of E bar dot dl bar over a closed surface. Actually, this will be equated to the EMF, and in its original form we say integral of E bar dot dl bar over a closed path is equal to minus d by dt of the magnetic flux, and this is called Faraday's law of electromagnetic induction. And then integral of B bar dot dl bar over a closed path is equal to mu naught times of the sum of the conduction current and displacement current. Just as we understand here, this is Ampere Maxwell's circuital law. This is modified form of Ampere circuital law. Integral of B bar dot dl bar over a closed path is equal to mu naught times of sum of conduction current and the displacement current in the path. This is Ampere Maxwell's circuital law, and these four statements together we call Maxwell's equations. So we can study much about this. We have very detailed explanation of each and every equation in our regular classes. We can understand that, and here only to mention about these equations, just we have made an attempt. So try to recognize the equation which corresponds to what, and then we will be able to answer our match the following question or conceptual question in our entrance examinations. So write these equations number of times so that quickly you will be able to recognize the equation.